Hi, welcome back to Probabilistic Programming 1. In the last video we've talked about model specification for our beer tasting experiment, and now we're going to talk about parameter estimation. So first we'll have a look at the data that's available to us. This beer tasting experiment is online at the Open Science Foundation, and we're going to use two packages called data frames and CSV to read that data. So CSV is for comma separated files, as in this extension. Have a look at this data set. It contains quite a lot of information, and for our purposes here we're only going to use the column correct identify. And as you can see, it consists of a lot of ones and zeros. Ones are for every time the participant got it right, and zeros are for every time they got it wrong. We have 57 participants, that's our sample size. And so if we plot the number of successes, so where the sum of times that the data set equals 1, and the number of failures, the sum of times that d equals 0, then we get this beautiful histogram, and we can see that the majority of participants correctly identified the alcoholic beer. But it's not perfect. There's still about 15 people that got it wrong. So let's visualize the likelihood of these observations. Before we dive into this graph, let's take a moment to look at what the likelihood function actually is. So I told you before that the likelihood of a single observation is a Bernoulli function, or Bernoulli distributions function. And I told you before that if you have independent observations, then you can take the product of the individual probabilities to get the probability for the whole data set. So what is happening here? Julia has list comprehensions just like Python. They start with square brackets, and then there's at the end there's a for loop involved. So there's a for loop that's contained purely within this part. So we're looping over our data set, our array with ones and zeros, and every element in that array, that's the xi outcome, and for every outcome we are computing the Bernoulli distribution's likelihood function. So that's theta to the power xi times 1 minus theta to the power 1 minus xi. So in list comprehensions you get a list out. Each of those entries is the function here applied to the element of the dataset D. And so we're taking the product over all of the elements in that list, and that becomes the likelihood for a specific value for theta. And then again we're plotting theta. We're plotting the likelihood for every theta in the range of theta that we specified. So that gives us this figure. You can see that the majority, so the largest mass under this distribution lies above 0.5. That reflects our earlier observation that the majority of students got it right. Another thing to note is that the y-scale is quite small. It goes up to 10 to the power minus 15. So I'd like to once again stress that the likelihood function is not a valid probability distribution, because the random variable that it is a distribution of is actually observed. So it is not a distribution at all, it is a function for this unknown parameter theta. Right, so now we'll move on to inference. We would like to compute the posterior distribution for theta. That posterior distribution is the fusion of our prior belief over what are possible values or probable values for theta, and then all of the information that we've gathered in our observations, so in this experiment. And the formula for computing the posterior distribution is one of the most famous formulas of all time, Bayes' rule. So there's the likelihood times the prior over evidence. You can get this tattooed in your arm if you like. So normally, in certain special relationships between likelihoods and priors, you don't compute the evidence. Actually, you're going to end up with a particular known form for the posterior distribution, and then you can renormalize with a known normalization term. And so in this example, in this beer tasting experiment, we have one of those special relationships. It's called conjugacy, and the beta prior distribution is actually conjugate to the Bernoulli likelihood function. And I'll show you what that means. So if you multiply the likelihood times the prior, in this case we'll get the product of the individual observations for this Bernoulli function, and then we'll multiply that with the beta prior. So the product over variables that are in the exponent becomes the sum over, so theta to the sum of those variables. So we get theta to the sum over xi times 1 minus theta to the sum over 1 minus xi. And if we use our earlier convenience variables, so s for the sum over x and then f for the sum over 1 minus x, we get this convenient form: theta to the power s times 1 minus theta to the power f times theta to the power alpha minus 1 times 1 minus theta to the power beta minus 1. So you can see this simplifies quite nicely, and this once again produces a theta to the power s plus 1 s plus alpha minus 1 times 1 minus theta f plus beta minus 1, and this is proportional to another beta distribution. So this is what conjugacy means. You can simplify the product of the likelihood and prior into a functional form which resembles, which is equivalent to the functional form of the prior. You'll notice that the normalization term for the prior has been left out, and now that we've recovered this functional form, we can renormalize to get a beta distribution. So that's also what we're doing here in code. Alpha 0 and beta 0 are the shape parameters of the prior distribution, and we're calling them 0 because they are the shape parameters of this distribution after 0 observations. And then we're updating the parameters after we made n observations, and they consist of alpha 0 plus the sum of, so the number of successes, so the sum of the data equaling 1, and beta of n is the beta of 0 plus the sum of data equaling 0. That's the number of failures. So we once again feed these shape parameters to a beta distribution, and then we plot that distribution. That shows us this. The red bar is the prior distribution. It's quite wide, it's quite dispersed. That signifies that we are quite uncertain about what probable values for theta are. After we've made these observations, the posterior is much sharper, it's much less wide, it's more centered around a single value for theta. And as you can see, it also reflects the shape of the likelihood quite a lot. That's because in this very simple model, this very simple setting, 57 samples in our data set is quite large. And Bert has already told you that as the sample size grows, the influence of the prior weakens. So the posterior distribution captures all of the available information and describes all values of theta. It tells us here that values of theta up to 0.5 are highly improbable, as are some of the largest values, and it is very probable that theta is somewhere in this range between 0.6 and 0.85. If we'd like to summarize this posterior distribution into a single value, a single point, i.e. a point estimator, then we usually pick either the expected value of this posterior distribution, the mean, and so because this posterior distribution has a beta form, it's a beta distribution, we know the functional form of the expected value. That's this thing. Another point estimator would be the maximal value of this posterior distribution. That's called the mode, and we could compute the mode through this function. You can see here that the mean and the mode are not exactly the same. They're very close, but they're not exactly the same. In some distributions they will be exactly the same, such as the Gaussian. The Gaussian is symmetric around its mean, and therefore that's also its mode. And here then they're not the same. So be careful when don't mistake the mean for the map estimate. Right, so the posterior contains a lot of information, and yeah, we've updated it from a very broad prior to a much sharper posterior. So at the end of the last video, I wanted you to quantify your own expectations of how well people can discriminate alcoholic from non-alcoholic beer. I wanted you to define your own shape parameters for the prior distribution. Now I want you to take those prior shape parameters, plug them in here, visualize this posterior distribution, and have a look at how your posterior differs from mine. And I'll see you in the next video.